everybody and welcome back to a new video in the audio data augmentation series. Last time we saw the theory behind different types of audio data augmentation techniques, both in the raw audio and spectrogram domains. This time we're going to take some of those techniques and implement them in Python. Let's roll. We're going to implement our audio data augmentation algorithms using Python 3.8. For following along, you'll need Matplotlib and librosa. And if you have any complaints from the interpreter regarding Matplotlib, probably you'll have to install Python 3tk, and you can do that on Bash using sudo apt install Python 3tk. But the sort of quickest thing you can follow along with this coding tutorial is by installing the dependencies using the requirements.txt. Okay, all that said, let's remove that. So what we want to implement here are these different audio data augmentation techniques in the waveform, in the raw audio domain. So we are going to implement adding white noise or Gaussian noise. We're going to be implementing time stretch and pitch scaling. Well, not from scratch, because pitch scaling, time stretching is a huge topic in itself. So we're going to be leveraging librosa for this. And then we're going to be implementing polarity, inversion, and random gain. So without any further ado, let's get started. So first we want to add white noise. So this function takes two arguments. So one is the signal, which is a NumPy array. It's basically our waveform, and the other one is the noise factor. So this is the sort of multiplier that is going to decide, the knob that's going to decide how much noise we want in our signal or mixed in with our signal. Okay, so the first thing that we need to do here is just create some noise. So how can we do that? Well, we can do that using NumPy. So let's import NumPy first, NumPy as np. So we'll do np.random.normal. So here we're basically going to have a noise, a vector creating using a Gaussian distribution, which is centered around 0. And then the standard deviation of our Gaussian distribution is going to be the standard deviation of the signal, of course. So we'll do a signal. We'll do a signal dot standard deviation, and then we want for the overall length of the of this noise vector to be equal to the length of the signal vector. So we want the two vectors to have the same number of items, and so we'll do signal dot size. So we'll pass this. Okay, so now we have our noise. So what should we do next? Well, for our augmented signal or noise augmented signal, what we want to do is take the signal and add to the signal the noise that we just created. So remember, these are two vectors, so we're adding basically two vectors here. Now, we don't just want to add noise as is, but rather we want to scale it with our noise factor. So let's do a multiplication. So we just multiply the noise by the noise factor, and then we add it to the signal, and finally we return the augmented signal. As simple as that. Cool. So now what next? Well, we want to showcase this thing and just let you see that it actually works. Okay, so we'll do a if name is equal to main over here. So we want to load an audio file that we have. Then we want to apply the transformation, in this case the adding white noise. Then we want to save the file, and then we want to plot the two waveforms so that we can see the difference, if any. Cool. So let's load the signal. For that, we're going to be leveraging librosa. So librosa. So we'll do a librosa dot load, and here we should pass the path, and I have, as you can see here, scale.wave file. The scale.wave file is a simple file that has a C major scale in it, performed on a piano. And that's what we're going to be using for like sort of practicing our augmentation techniques. So let's listen to this file first, just as reference. Yeah, very standard scale on a piano, C major scale. Cool. Okay, so we'll load this scale.wave file, then we'll derive the augmented signal, and we'll do an add white noise. We'll pass the signal as well as a noise factor. So let's say 0.1 for our noise factor. Oh, by the way, here when we load with librosa, not only we get the waveform, but we also get the sample rate back, which is defaulted in this load function to, I think, 22,050 Hertz. Okay, so now we have the augmented signal. The next step is that of writing this augmented signal. So we want just let's save it. So how can we save it? Well, for that, we'll need to import sound file as SF, because this has some facilities to write wave files. So we'll do a sf.write, and here we should pass the file, and we'll call it augmented.wave. Then the data, which is the augmented signal, right? And finally, we need to pass the sample rate here. Right, so one last thing that we want to do here is just to plot the signal and the augmented signal to check the differences. So I already wrote a function here, which we can import. So from helper, we can import this plot signal and augmented signal. Now let's jump into this like real quick. So I'm not going to write this from scratch, because the point of this tutorial is about audio data augmentation, not about like plotting waveforms. But you have it here for reference. We basically use matplotlib as well as librosa display waveplot to display both the signal and the augmented signal. Okay, that's it. So we're going to just pass this plot signal and augmented signal, and we need to pass as arguments the signal, the augmented signal, as well as the sample rate. Okay, so now we are ready to run our first transform. So let's see how it goes. So we are going to be running this script, and here we go. We have our script. So this is like the scale. So we have the two waveforms. So in the top part, we have the original signal, and down we have the augmented signal. So these are like all the different notes on the piano, right? And as you can see, we added some noise, because take like this first part, which is absolutely like silence, like in the original sound. So here we have like a lot of like white noise. You can't really see that like in the actual like notes, because they are like already quite noisy, like the waveform is quite noisy, but like here in the end and at the beginning you can clearly see that we added like some noise. Okay, so let's close this and let's listen to the augmented file that we just produced. And here we go. Definitely have white noise there. Okay, yeah, that sounds good. So just like to show you that if we change this noise factor, say to 0.5, the white noise is mixed in, is going to be way more prevalent. So let's rerun this. Okay, yeah, you can already see that noise is more significant, because sort of like a thicker here, like in the waveform, right? But let's close this and let's listen to the result. Yeah, here we go. Yes. Almost unlistenable, right? Okay, yeah, so let's close this, and now we have a function that adds white noise. Of course, you can add other types of noises, like for example environmental noise or background noise. So in that case, you need to load the environmental noise and mix it in, like add it, just like this, but rather than having like white noise here, you're going to have like your loaded noise or environmental noise that you probably recorded somewhere or downloaded somewhere. Okay, next step, time stretch. So as I said here, we're not going to implement this from scratch because this is a big topic. So we're going to be using librosa. Just because I mentioned it, so we already have it up here because we imported. Oh yeah, we imported because we use this for loading, right? But so let's create this new transform here. So time stretch. So time stretch takes a couple of arguments. So the first one being the signal, of course, and the other one being the let's call it the stretch rate. So this is by how much we want to speed up or slow down our signal. Okay, so here we'll do a return and we'll be using librosa.effects.time stretch, and here we'll pass the signal as well as the stretch rate. Okay, so now let's try this one. So let's do time stretch signal. Okay, yeah, let's use like this stretch rate. So 0.5. So this is going to stretch this is going to slow down in half the duration of our signal. So let's run this and see if it works. Okay, so here we go. Yeah, so you can see here that the original signal and the augmented signal. Oh yeah, let me just scale this up. Okay, you can see that on the time axis, the original signal lasts for 9 seconds, 10 seconds more or less, whereas like the augmented signal, the time stretch signal, it's basically like a factor of 2 of that. So it's almost like 20 seconds. Right, so now let's listen the results. So let's listen to the original one for reference. Yeah, so this is the original speed. Okay, so it's sort of like slowed down to half the tempo and the pitch is basically the same, but you could hear that there was like something like weird, like in terms of like the attack. It wasn't like super sharp, and that's because this time stretch and pitch scaling algorithms tend to sort of like degrade the quality of the signal if they are abused. And of course, like stretching down to half a signal, it's quite a lot, and this is like the point of like credibility. So you can't abuse these transforms, so you have to be like very subtle like in the changes that you want to apply here. So these basically would be like no good, like stretching like in half. So what I would suggest you doing, like it's basically like being like between like a stretch rate of 0.8 and 1.2, like something like that, not more than that. That probably is already too much. Next, let's implement pitch scaling. For that, we're going to be using the same approach that we use for time stretching. So we're going to piggyback on librosa pitch scaling facilities. Okay, so we'll do the fine pitch scale. So we'll pass as arguments the signal, the sample rate, and the number of semitones we want to scale up or down our signal. So if it's a positive number, so we're going up. If it's a negative number, we're going to be going down. So from C major, say +2, we're going to go to D major scale. From C major, 1 semitone down, we're going to go to C, to B major, right? Okay, so let's return librosa.effects.pitch shifts, and here we should pass the signal, then the sample rate, and the number of semitones. So let's see if this works. So here we're going to pass pitch scale, so signal, then the sample rate, and finally the number of semitones. So let's say we're going to go +2. Okay, so from C major, the scale is going to go up to D major. Okay, let's run this and see the results. Okay, so here, yeah, we just have like the two waveforms. Yeah, it's difficult really like to tell the difference, but let's just like listen to the results. Compared to this. Right, it just went up, so that was a D major scale. Right, now let me show you the issue with these algorithms when abused. So when used like scaling like too much. So you say, for example, we want to go up 24 semitones. So it's basically 2 octaves. It's the same C major, but 2 octaves above. So let's run this. Here's the result. It's no longer a piano, right? It sounds some sort of like chip MIDI distorted guitar sound, but it's definitely not a piano. Well, that's because, I mean, like these algorithms like sort of like degrade timbre. So you have to be like very attentive when you decide how much to use them. So in this case, when you're using pitch scaling, well, just use it with caution. So go up like 4 or 5 semitones and down 4 or 5 semitones, not more than that, because otherwise it's gonna start like sounding like weird. It really depends on the algorithms. Better algorithms are going to be able like to maintain like sound for like greater like ranges, but still, I mean, be sort of like subtle when using temp stretching and pitch scaling. Okay, so now next we have polarity inversion. So this is extremely simple to implement because literally we have to take the signal and multiply it by -1 so that will flip horizontally the waveform. So let's do that. So we'll create this new function called invert polarity, and here we'll just pass the signal in and we'll return the signal multiplied by -1. That's it, like as simple as that. Now I'm not gonna test this one because you're not gonna be really able to hear like any major difference or like see the difference like with such like a complex like waveform. But yeah, it's as simple as that. Now the last thing that remains to be implemented, well, let me just like give a couple of blank spaces here. It's random gain. Okay, so we'll define a random gain. Right. So here we need the signal. We want a minimum gain factor, and a maximum gain factor. Okay. So what should we do here? Well, first of all, we should sample a random float value between the minimum gain factor and the maximum gain factor, and for that we'll use a random uniform. So we'll do gain factor is equal to a random dot uniform, and we'll pass in minimum gain factor and maximum gain factor. And so this is a uniform distribution that's going to sample a value within a certain range. And here we have our gain factor, and then what we need to do is quite straightforward. We take the signal and we multiply it by the gain factor so that we can scale it, right? So we're basically like working on the amplitude, so we're just like reducing it or just like extending it, right? Okay, so now let's try this one. So we'll pass a random gain, and so here we're gonna push it up. So we'll just put like minimum gain factor 2, maximum 4, right? And let's hear the result. So let's see. Okay, and now Just like take a look at the scale here, like on the y-axis, like the amplitude. So here, the original signal is between -1 and 1, whereas the augmented signal that's been sort of like amplified has a different range here on the y-axis. So the amplitude goes from, say, -3 to +3. So we just increase the volume in the end, right? So let's listen to it. Yeah, it's clipping. So once again, when you do these transformations, just be very subtle, unless you want some sort of like distortion like this. So this is another type of augmentation that you can apply, where you take a signal and then you sort of like clip it, like you have a clipping distortion. But if you want just like to change the gain, the amplitude somehow, but still have it like a recognizable sound, well, you have to be like very subtle in the way you use, in this case, like the minimum gain and maximum gain factors. So here you have them. 5 different techniques implemented, some of them from scratch, others using a librosa. Now, what's next? Well, the next step will be that of taking a look at the different libraries that you have available for implementing audio data augmentation. So stay tuned for that, and until next time, take care.